Hello. So in this lecture, we will be looking at building decoders for the 7.4 Hamming code. You remember in the previous MATLAB coding lectures, we saw how to build decoders for the repetition code. We built both the soft decision decoder and the hard decision decoder. We ran them and saw what the output was and compared it with some plots, and we got good answers. We will do the same for the Hamming code. I will build it very quickly and show you. But a couple of things I want to point out, once again remind you, the code I write primarily using MATLAB for the demonstrations. You can use Octave as well, and the same code that we provide for you should work on Octave also. Okay, so let's get started. So this is the Hamming code, the 7.4 Hamming code. I mentioned that this is a linear code as well, and one can write down the generator matrix for this linear code. So this would come out like this. So you have G equals, remember it is a 7.4 code, so it will be 4 by 7 generator matrix. Okay. So it turns out since this encoding is systematic, you can quickly write down the generator matrix. So the generator matrix will look like this: 1 0 1, and then you have 0 1 0 0, and 1 1 1, and then you have 0 0 1 0, and 1 1 0, and 0 0 0 1 0 1 1. Okay, so this is the generator matrix for this 7.4 Hamming code. So you have, when you multiply m with g, you have the message bits appearing in the first 4 locations, and then the first parity will be m0 plus m1 plus m2. The second parity will be m1 plus m2 plus m3, and the third parity is m1 plus m2 plus m4. Okay. So this is a generator matrix. One can write down the parity check matrix as well for this code. So that will be just P transpose and I3, and one can use it. Okay. So I'm giving you this just for completing the previous lecture, but this you might want to use it in your coding. For instance, when you want to do encoding, this is a good thing to use. Okay, so let's move over to MATLAB. So I'm going to first save this as 7.4 Hamming. Okay, so we'll use the same 6 dB. Remember the rate is 4 by 7. Okay, so let's make a few quick changes here. This part does not change. K equals 4, n equals 7. The number of blocks, maybe we want to keep it at some low number just for simulation. This part is okay. The message is k bits. Now the code word I have to change, right? So I have to have the message appearing by itself. Okay, and then remember, from my encoding, my message will come here by itself. The 4 bits of the message will come here. What about the first parity? It is the first bit of the message XORed with the second bit of the message XORed with the third bit of the message. Okay, so that is my first parity. So I can write that down here. So it's going to be MSG of 1 plus MSG of 2 plus MSG of 3, and then I have to do modulo 2, and that you can do in this fashion. Okay. So this is for the 7.4 Hamming. Okay. Now just to make the writing a bit clear, I will use this dot dot dot, which gives me the ability to write over multiple lines. The second message, second parity bit, if you look at it, is actually the second message bit XORed with the third message bit XORed with the fourth message bit, right. So one can write that down. Remember this mod 2 you have to keep doing, okay. And the third parity bit, I'm sorry, this is going a bit too far, okay. The third parity bit, if you look at the equation once again, it is the first message bit XORed with the second message bit and XORed with the fourth message bit, okay. So, one can write this down as MSG of 1 plus MSG of 2 plus MSG of 4 and comma 2, that is it. So, I have done my encoding, okay. So, 1 2 3, 2 3 4 and 1 2 4. So, let us check that once again, that is exactly what it is, okay. So, that is done, okay, you have done the encoding. You can write this a bit differently, you can store the generator matrix and do it if you like, there are various ways of doing it, okay. So, after this the bit to symbol conversion is straightforward, it is the same thing, nothing needs to be changed. This gives you the symbol vector and then this gives you the received vector, right. I am creating noise of Gaussian distribution, multiplying with sigma and then adding it to this. Now, hard decision decoding, the threshold at 0 is the same, but this condition is not going to be the same, right. So, you need to have something different here, it can't be the same as this, we will have to do something different here. So, let us delete this. Same thing with soft decision decoding, this cannot be the same, this will have to vary a lot, okay. Remember what do we do in hard decision decoding, you have to find the distance of the hard decision vector B from every code word and find that code word which is closest to it, okay. So, that is the task in hard decision decoding. In soft decision decoding, you have to find the distance between the received word, right, real received word and all possible symbol vectors, right, and then find that symbol vector which is closest to the received vector in Euclidean distance, okay. But we also saw in BPSK case, instead of finding the Euclidean distance and finding the minimum symbol vector, you can take a dot product and find the maximum dot product. So, which symbol vector has maximum correlation with your received vector, okay. So, that is also something that you can find, okay. So, once we will do it in that fashion, we will do soft decision decoding in that fashion. I will take dot product with all symbol vectors and pick that symbol vector which gives me the best one. So, for both these things I need the list of code words, okay. So, I need the list of all code words of the Hamming code and I want to store them in some in a vector and then use it, okay, and also all symbol vectors, right. So, both of these I need. I am going to generate it for small code words, codes like this one can quickly generate, it is not very difficult to write a piece of a few lines of code to generate these code words, but in general if you have larger code it might be difficult and it will not work, okay. But nevertheless let us get started with generating these code words, okay. So, I'll describe how I usually generate code words. This is not the only way to do it, there are so many other ways in which one can do this. So, one can write down the generator matrix, okay. So, let me take some help from what I had before, 1 0 1 1 1 1 1 1 0, okay. Okay. Let us check 1 1 0 0 1 1. Okay. So, you can check that this is the generator matrix that I had before, alright. So, now I have to multiply with the message bits. How many message bits do I have? I have 4 message bits. So, there are 16 possible binary vectors. So, how do you get a list of 16 possible binary vectors? So, it turns out there is this little command here which I use. There are I am sure other possibilities here. So, if you do this, this will give you the list of all binary vectors in MATLAB. Okay. So, 0 0 0 0 0 0 0 1 0 0 1 0. So, the problem is this is a string and it turns out I want to convert it into vectors, right. I do not want a string, I want a matrix. For that I use this little trick. I usually subtract it, I think 47 would do it, no maybe not, 48 would do it, okay. So, if you do DEC to BIN and then you subtract 48 from it, MATLAB does this conversion from strings to bits, at least if you have 0 1, this is a good enough trick to use. So, I will do this. So, this gives me the vector of all possible binary sequences of length 4. Okay. So, you might have other ways of generating this. So, I am just generating it like this, okay, 0 0 0 0 0 0 0 1, so on till 1 1 1 1. Okay. This is 16 vectors are here. Okay. So, let us store this. We do not need to necessarily store this, we can just get this and then multiply with g on the right. Okay. But we have to do modulo 2. If you do not do modulo 2, you will not get right answers. Okay. Mod of this comma 2. Okay. So, it turns out this is the list of all code words that I want. Okay. So, this is the list of all code words in the Hamming code. So, you see I found all the binary sequences of length 4, I multiplied with g, I did a modulo 2, I got all code words. Okay. So, you can check if you like that you got the code words. Okay. So, now I can do a simple cut and paste from here to my editor window. Okay. So, one can, I mean, one need not do it inside the simulation block, you can do it outside. I can call it okay, code words, okay, or you can use any other notation that you like. So, here I can paste it. So, it is good to put semicolons to indicate that the. So, I want to immediately point out this is something that you cannot do for long codes. Okay. So, if you have say k equals 100 or 1000, this will be 2 power 100, you can't list out all the code words like this, but for us it is okay. So, this is a small enough operation, you can do it very easily. Okay. So, once I have the list of code words and I have my hard decision vector b, it is relatively easy to write down the hard decision decoding. Okay. So, I have to find the distance between this vector b and every code word in my array C words. Okay. So, I had the list of all code words, I have to find the distance between this and that. Okay. So, even for this I am going to use a little bit of a device here, it is just to get it done very quickly. So, I can do this repeating the matrix. Okay. So, I will do it 16 times 1. Okay. So, this will create a vector of b repeated 16 times. Okay. You can try this out if you have a installation. Okay. And then I will add it to C words and do a modulo 2. Okay. This will give me the XORs, I am XORing B with every possible code word. Okay. And then what do I do? Okay. So, this gives me just the XORs of all the code words, and now I can look at the weights, right. So, this I will call as the distance array. Okay. So, this is just the XORs. So, how do I find the weight? So, it turns out you can multiply a vector on the right okay, and this will give me the distances. Okay. So, I will illustrate it maybe later on and you will see how this works out. So, I am repeating the received vector b 16 times, I am doing XOR with each code word, I get a list of XORs, they are 16 in number, each is a vector of length 7. How do I find the weight of that now? I multiply on the right with ones of 7 comma 1. So, it simply multiplies and adds up and gives me the weight. Okay. So, I am not done now, I have to find out of all these guys the one which has the least distance. Okay. So, that one can find using this min. So, min d comma position equals min of distance. Okay, of all these distances, which one is the minimum? Okay, so that's this solves, and then once I know POS, the minimum itself doesn't really matter. I can find message cap 1 as C words of pos comma 1:4. Okay. So, hopefully this was clear to people. I wrote it down a bit quickly. Think about what I am doing. I am finding the distance between B and every possible code word and finding that code word which is closest, okay, minimum distance between this and that. Okay. So, let us do, so we will run this. I have to check if I made any mistakes or not. Maybe I made a mistake. So, we will, when we run it, we will know if it causes any errors. We will go in and look at it and check it out. Okay, so we will do that at that time. So, for soft decision decoding, it is sort of similar, except that the distance is going to be, it is not distance, I will call it correlation. Correlation is going to be with the received word R, but I am going to have the list of symbol vectors. So, it is 1 minus 2 into C words multiplied by the transpose of R. Okay, so this will give me the list of all correlations, and I once again find min and pos, but in this case I have to do max of correlation, and then what I have here is the same. Okay, so MATLAB is pointing out that okay, so maybe I will call this mn1 and mn2 just to keep MATLAB happy, and then this is just a way of counting errors. Maybe I will use the hard decision decoder first. Okay, so let us see how this works. So one useful thing I do usually when I run this is I put a breakpoint here, and then I run it to see what is going on. So maybe we will put lower EB over N0, and then let us just run it. Okay. So, it has come up to this point and stopped, and to see what it is doing, you can go here and look at the message that was generated 1101, the C word that was generated 1101,001, and then S, which is -1, -1, etc., and then R. Okay. So, you can see noise got added, a lot of things have happened. It does not appear that there has been an error, okay, but nevertheless let us see what happens. Okay. So, this is R. Okay. So, I am going to run one step. So, I will get B. Okay. So, let us check what B is. Okay. So, it sort of agrees with the code word here, but nevertheless let us go through with what the decoder is going to do. It is going to find distance. Okay. So, let me show you how this worked. It gave you an array of distance, and it tells you what the distances are from every possible code word. Okay. Okay. So, how did it work? We did this rep mat of b comma 16 comma 1. Sorry. Okay. So, it repeated the same received vector 16 times, and then I did a XOR of this with my C words. Okay, so this gave me all the distances. Okay, how do I find the weight of each of these guys? I simply multiply on the right with ones of 7 comma 1. So, this gives me this vector. Okay. So, this is the same as my dist vector. Okay. So, the next step finds the minimum and then sets the message cap. So, let us check what it did. The position is 14 and message cap 1 agrees with the message. Okay. So, this is how the decoder worked. So, let us see if my soft decision decoding is implemented correctly or not. The first step is the correlation. Okay. So, remember it works with the soft decision decoding. So, correlation will be number Okay, so you see you get a whole bunch of numbers. The next step is the max of the correlation and then assigning message cap. So, if you look at pause, again it's 14 and message cap 2 and message also agree. Okay, so it's just a easy enough calculation. So, this is something that I typically do, just continue and you can quit debugging. Okay. So, you can clear these things. So, it looks like things are working fine. So, let us maybe pick EB over N naught 4 and then run this and then see use for the hard decision decoder, see what happens. So, let me just save this. I have EB over N naught 4. I am going to run it now, BPSK 74 Hamming sim. So, let us do this format short G. Okay. So, we get 0.01. There were 4000 bits that were transmitted. Remember, we did 1000 blocks of 4 bits each. Code word is 7000 bits, but then 4000 bits is the message bits. There were 61 bit errors, okay, and you got this. Now, it turns out one more error to track, which is very important, is the block error rate. Okay, so far we did not have to do it. We were just looking at message errors. So, this I will make a little bit of a modification here. So, this I will make as n bit errors and MATLAB does this thing of being able to convert everything, which is good. And then I will have n block errors, which is also 0, which will be I mean how many code word errors you have. So, what will happen here is so I'll count this n errors as sum of this guy. Okay. So, this is the error in one block, okay, and if n errors is greater than 0, if there is an error, okay, I will add n bit errors as this and n block errors equals n block errors plus 1. Okay. So, once again what am I doing here? I am looking at if there was an error in this block. If there was an error in this block, I am incrementing n block errors by 1 and then n bit errors by number of errors. Okay. So, this is a simple way. BER is this and FER sim is actually n block errors by n blocks. Okay. So, this is the frame error rate. Just like I report bit error rates, I have to report the so BER came out this way. So, I will just make a few adjustments here. N block errors can be output. I will put out FER sim, BER sim, bit errors, maybe the bit errors can come later, block errors and then n blocks. Okay, so, I made a few changes here. I am tracking block errors as well. You can see how I have tracked block errors here. I am counting the number of errors in a block. If there were any errors in the block, I am incrementing the number of block errors by 1 and number of bit errors by n errors. So, this is also something important. BER, FER, we run this. So, I do not think I have made any changes here which are problematic. So, let us run it once again. So, you get more answers. So, there were so you can see we ran 1000 blocks. Okay. There were 34 block errors, 56 bit errors. Remember, every block error may correspond to 1 or more bit errors. So, number of bit errors will be greater than the number of block errors and the block error rate is 0.034, bit error rate is 0.014. Okay. So, as a figure of merit, you should have at least like 20-30 blocks in error. Okay. So, that is a good number to have to get a good reliable statistic. Okay. So, you can do the soft decision decoder as well. So, how do I check for the soft decision decoder? I can simply change this to 2. Okay. So, if I change this to 2, I should get the soft decision decoder. So, let us run the same thing and you can see it is significantly better. Okay. The soft decision decoder is almost an order of magnitude better than the hard decision decoder. There were just 5 block errors out of 1000 and bit errors were just very small in number. Okay, so that's the magic of doing soft decision decoding, and you can see clearly soft decision decoding is significantly better in the Hamming code. Okay, so you can see how this encoding and decoding has worked for small codes. This is something you can do. For instance, the 6,3 example that we saw in the lectures, you can make a quick modification here to change the encoding and change the decoding. The list of code words will have to be changed, and you will get your decoder to work. Okay, so that's the end of the simulation for 7.4 Hamming code. Hopefully, you can take this template and modify it for other small codes as well. But however, if the code size becomes really large, this is a difficult thing to implement. Okay, so we'll stop here for this lecture, and the next lecture will be a very nice and important bridge between the modern codes and the starting point of classical codes. We will take two codes and look at their decoders in very closely and think about them and how they can be used in multiple ways. Okay, so the two codes we'll use are very simple codes, the repetition code and what's called a single parity check code. These two are very crucial. They play a very important role in the bigger decoders, in the very popular decoders for modern codes. Okay, so we'll do that in the next lecture. Thank you very much.